As this heading shows, we're going to be talking about modern portfolio theory building blocks. And there is a handout that you need to retrieve in order to watch this video and get much out of it. So if you don't have it in front of you, just turn off the video and go find it. It's on the website, of course. The reason we care about modern portfolio theory for this course is because Chapter 13 addresses the security market line. The security market line is part of the capital asset pricing model, and we're going to use that to calculate the cost of equity when we get into Chapter 14. The security market line and capital asset pricing model actually is developed from what was originally, was termed modern portfolio theory. The security market line founder or discoverer or inventor received a Nobel Prize, as did the person who came up with this, which is essentially, not this very thing, but in a couple of pages, which is essentially the mathematics of risk diversification. So let's talk about it. What we're showing here is mean and standard deviation. Mean is the expected value in this case. So what we have here is a set of returns and a set of probabilities. And the expected return is equal to the sum of each probability multiplied by its respective return. And then we add them up. And that's the expected return. The standard deviation says we're going to take the deviation from the mean for each one of the returns. Take that deviation, then square it, then multiply it by its probability of occurrence, and then add them all up, and then take the square root. Sounds like a lot, and I suppose it is, but we're going to plow through it. So here's our probability distribution. We have a 10% chance of a minus 10 return, 20% chance of a 0 return, 40% of 10, 20% of 20, 10% of 30. Now I have these equally separated by 10 units, and this is a nice symmetrical distribution with 4 in the middle and 2's and 1's at the end. So we have a symmetrical distribution and evenly spaced returns. Well, what this says to do is take every probability, multiply it by its return, and then add them all up. So minus 10 times 0.1 is minus 0.01. 0 times 0.2, 0. 0.1 times 0.4, 0.04. 0.2 times 0.2, 0.04. And 0.3 times 0.1, 0.03. Add them up, as this says to do, and we get 0.10. So that is our mean, our expected return. This next column, I have a mistake here. The numbers are right, but this 2 should not have been here. So on your page you see a 2, and I've already blacked it out. So what this says is to take every return and subtract from it the expected return. And that is our deviation, from which we're going to get a standard deviation. So each deviation, so here's our return column, and here's our mean return. So minus 0.1, subtract 0.1, it's minus 0.2. 0 minus 0.1, minus 0.1. 0.1 minus 0.1, 0. 20 minus 10 is 10, and 30 minus 10 is 20. So now we have the stuff that's in the parentheses. And then it says to square all that stuff. So minus 0.2 squared is 0.04. 0.1 squared is 0.01. 0 is 0. 0.1 squared is 0.01, and 0.2 squared is 0.04. And then it says multiply each one of those squared deviations by the probability associated with that particular return. So we're going to take this number and multiply it. Let's see if I'll use another pen. We're going to take this number here, 0.04, and multiply it by this probability here, this probability here, and it's 0.1 times 0.04 is 0.004. And 0.2 times 0.01 is 0.002. And 0.4 times 0 is 0, and 0.2 times 0.01 is 0.02, and 0.01 times 0.04 is 0.04. Now you notice that this is symmetrical, and it's only the case because this stuff is. And essentially what's happening here is whatever we have up here we're going to have down here, only because this is a nice simple version. So what it says to do then is add them all up. That's what this summation says. So we add up all of these squared deviations times the probability. We add them all up, and that gives us our variance, or sigma squared. And when we take the square root of that, we get the standard deviation. So the calculator doesn't have a nice way to solve this. We pretty much just have to plow through it, just like this in tabular form. Now this is when there are probabilities. I will refer to this as ex ante. Ex ante means, roughly speaking, before the fact, or from before, literally. And that just means we're looking toward the future, and that's pretty much what we're doing in corporate finance. We're trying to figure out probabilities of things that will happen in the future. This next page is ex post. Ex post would be from after. And so we're looking at things that have already occurred. Again, we have standard deviation, but we're going to calculate it differently. So let's take a look at this. Our mean return is equal to the sum of all the returns. So every return for asset C, and I'm just labeling it as asset C, in time t. That is, we're looking over time. We changed index from I to t, and that's wasn't really necessary, except usually for time frames they use a t as the index. And we go to time n. And in this case we're going to have 5 periods, so it's time 1 to time 5. And this says exactly what you did in 3rd grade to calculate the average. Add them up, divide by however many there are. That's all there is to it. That is our arithmetic mean return. Now we've gone through geometric mean before, and it's different, and it's going to be less than or equal to the arithmetic mean, and it's only going to be equal if all the numbers in this series are the same. And so what we do here is we take our return in decimal form and add it to 1 for each period t. So 1 plus r for each one of the periods. This says multiply them together, not add them, but multiply them together. Then take the nth root, that would be in this case the 0.20 or 1 over 5 or 0.20 because there are 5 of them, and then subtract 1. And we'll do that in a minute. And the standard deviation is different also. We take each one of the actual returns and subtract from it the arithmetic mean return. Those are our deviations. We're going to square our deviations. We're going to add them up, and we're going to divide by n, and then take the square root, and that's going to be our standard deviation. Now, note that before, in the previous version, I'm flipping back to the earlier page, we were multiplying by probability, whereas here we're dividing by n. Let me see if I can get these both on the page at the same time. Well, actually, if all the probabilities were equal, you would be multiplying by the same number, and if they were all equal, that number would be 1 over m. That is, there are m different possibilities, and if they all are equal, have equal probability of occurring, then 1 over m would be their probability. And so this would be 1 over m, which means you can take it out of here completely and just divide by m. And that's kind of what we have here. We're using n instead of m, but it's the same concept. So now what we're going to do is just trudge through this, and we have 5 different outcomes, and they've already occurred ex post. We had a return of 12% in the first year, and minus 12 in the second, and 24 in the third, and 10 in the fourth, and 16 in the fifth. And if we add up those numbers and divide by 5, we get 10. So 10 is our mean return. And then this says, well, take all the deviations. So we're going to take the deviations. 12 minus 10, 2. Minus 12 minus 10 is minus 22. 24 minus 10, 14. 10 minus 10, 0. 16 minus 10, 6. And then it says, once you have the deviations, square them. So 0.02 squared is 0.0004. Minus 0.22 squared is 0.0484. Notice that we're always going to have non-negative amounts in this column. If we have a 0, as we do down here, squaring it will give us a 0, but any other number squared is going to be positive. Like this is going to give us a positive number. Continuing, we've got 0.14 squared is 0.0196, 0 squared is 0, 0.06 squared is 0.0036. And then it says add them up. So we're going to add them up. And then it says divide by n. So we're going to divide by n, and when we do that, we get the variance. So without the square root, the radical, this would be sigma squared, and that's variance. And then if we take the square root, that gives us the standard deviation. Now, when it shows as a sigma like this, sigma is the standard deviation of a population. And one could argue that this is a sample, and so we should use S instead of sigma, and we would divide by n minus 1. And if we did that, we'd come up with the sample standard deviation. Now this just shows the geometric mean calculation, and what we're going to do here is calculate 1 plus r, remember, 1 plus r, for each one of these cases. So 0.12 plus 1 is 1.12. 1 plus a negative 0.12 is 0.88. That's the one that will always cause a problem. 1 plus 0.24 is 1.24. 1.1, 1.16. Multiply them together, and that gives us 1.56. Take the nth root. The nth root is 0.2. The exponent would be 0.2. Subtract 1, and that gives a geometric mean return. This sort of fudge rubbed out here. It wasn't supposed to be. It was highlighted, and I can't find the original to this whole thing. And all this is saying is if you did it in Excel, it would come out like this. Now, I'm going to do the geometric mean. I'll have to zoom out a little bit here. It'll be harder to see. Maybe. I'm going to calculate the geometric mean on my calculator so you'll know how to go about it. And I'm just going to check here and see if something's in here. Okay, so I'm going to say 1.12 times 0.88 times 1.24 times 1.1 times 1.16 equals. And of course this is rounded here, but carrying it to all the places, we would say this number needs to be taken to the 0.2 power because there are 5 outcomes, so it's 1 over n, and 1 over 5 is 0.2. So I'm going to hit the y to the x key, y to the x, 0.2 equals, and then I'm going to subtract 1, minus 1 equals 0.0929, and that's our number down here. Now, actually, there's something else to be seen here. What if we were to invest $100 at the beginning and then over 5 years we earned these returns with these 1 plus r's. These are holding period return relatives. How much would we have at the end? Well, if we started with 100 and then multiply that by 1.12 and multiply that by 0.88 and multiply that by 1.24 by 1.1 by 1.16 equals 155.95. In other words, at the end we would have $155.95. Now, if I were to call that a future value, and I were to call my 100 a present value, and if I had 5 time periods, I might wonder, well, what rate of return would I get? Would I have gotten? Because it's in the past. So I'm going to say compute IY, and I get 0.092936, the same result. Now, this averaged 10%. What if I had earned what if I had earned 10% every period? Well, it would have looked like this. Let me clear everything out here. 100 times 1.1 times 1.1 times 1.1 times 1.1 times 1.1. Oops, I'm going to multiply that by 1, and it equals $161.05. Now notice, if I had gotten 10% every period instead of an average of 10, this is still an average of 10%, it was 10% every period, but if I had gotten 10% every single period instead of this variable version, I would have ended up with more money at the end. And guess what that rate of return would have been? Well, let's put this as our future value, and 100 change signs as our present value, and 5 is our n, and when we compute IY, 10%. So our geometric mean, if every year is 10%, it's going to be 10%. Not so with our arithmetic mean. Excuse me. I don't have COVID-19, I have allergies. Now, we can also calculate our standard deviation using our calculator. So, this might be a little bit more difficult to follow. So let's see what we can do. I'm going to go into data. So I'm going to hit second data. And then go ahead and hit second clear TVM and second clear work just to get rid of everything. And then let's go back into data. And if I hit the down arrow, it's going to go from X to Y to X to Y to X to Y. I want it to be on X for right now. Now this is set up to take 2 sets of numbers. We're only going to look at 1 set of numbers. So for the second set, the Y values, we're just going to enter 1 for all the outcomes. So here's what we're going to do. We're going to put in all these, and then we're going to calculate a mean and a standard deviation using our calculator. So going back to it, it's second data, that's the 7. And you want to check to make sure that you haven't left anything from a previous problem. You haven't done a previous problem, so you shouldn't have anything in there, but you will eventually. And now we're going to enter our data after I take a drink of water. So, 0.10. Sorry, that's 0.12. Enter, down. And now it wants a Y value. This is a little bit, let's see if I might have to put something under there so you won't have that, maybe that'll work. And the Y value, we're going to go ahead and let that be a 1. So we're going to hit the down arrow again. And because of that interruption, why don't I go ahead and try it? I'll start over again. So I'm going to go second, data, and there's nothing in there. And for the x's, I'm going to put in my values, and for the y's, I'm just going to put in a 1, and the 1 is, or a 0, whichever number already comes up. So let's give it a shot. 0.12, enter, down. And the y, I'm just going to say enter, down. And now it wants my second one. 0.12, change signs, enter, down. And the y is just going to leave it at 1, enter, down. And then the third one is 0.24, 0.24, enter, down. And the third y, enter, down. The fourth, 0.1, enter, down. And the y value, enter, down. And finally 0.16, enter, down, down. Now, from here, we're going to go to stat, which is the 8 key. So we're going to go second, stat. And this shows LIN, which suggests that we're going into linear regression. We're not just yet, because we're only looking at one set of numbers, not two sets together. But we're going to hit the down arrow, and it's going to say n equals 5. Well, that's good to know, because we thought we put in five sets of values. So far so good. Now I'm going to hit the down arrow again, and it says x bar. That's our mean. Our mean is 0.10, and that's what this says. If I hit it again, it says sx. Now if I go down one more, it says sigma. Lowercase Greek letter s is sigma. Sigma x is 0.12, and that's our 0.12 here. Now if we had divided not by 5, but if we had divided by 4 here, we would have gotten not sigma but s. So we would have divided by n minus 1 and taken the square root, and that would have given us our standard deviation of a sample. So that's how we're going to use our calculator, and we're going to go through another example in a couple of minutes. So if you didn't quite follow that, you might want to back up the video and watch it again. Very important that you be able to do this on an exam, because it takes a lot of time to do this in tabular form. You're much better off to be able to put it in the calculator, and you're much more likely to get it right. Now this, let me zoom in a little bit, this goes to portfolios. So the idea here is we're putting two assets into a portfolio. And what we have here is another version of expected return. And this is expected return of a portfolio, the subscript P. And this says take all the expected values of the different assets in the portfolio. And for every one of those expected returns, did I say expected assets? Expected returns. For every one of those expected returns, we're going to multiply the expected return by its weight. And the weight is just what percentage of my money is in that particular asset. And all the weights need to add up to 100%. Everything has to be accounted for. So I'm going to take each return and multiply it by its relative weight, and then we're going to add them up, and that's our expected return. Now we've got another concept here, and this is covariance, and it's related to correlation. And I'm not sure how much you learned about covariance in your statistics course, but it means just pretty much what it says. How do things tend to vary together, to co-vary? And what we have here is, in this paren, I've got two sets of returns here for C and for D. And I have 5 different time periods. And what this says is, for every period, take the deviation from the mean for C. So we've got C's return, mean return is 10, D's return is 15. And for each one of them, we're going to take the difference between the return for that period and the mean return. And for the same period, we're going to do it for D. So what we have is the deviation for C in period 1 times the deviation for D in period 1, and then for period 2 and 3 and 4 and 5, and we're going to add up all those products. Now, note that if this number here is positive, it means that the return for that period is higher than the mean. That would give me a positive. And if this one is higher than its mean, it would also give me a positive. Positive times positive, positive. If they were both below the mean, then this would give me a negative number. This would give me a negative number. Negative times negative, positive. And the more they do that, the more that when one's above the mean, the other's above, and when one's below, the other's below, the more they tend to move in the same direction, up or down. They would have a higher degree of covariance. Now we take all those products, we add them all up, divide by n, and that gives us something called a covariance between asset C and asset D. And so here's what we've done. Just calculated the mean value here, calculated the mean value here. These two numbers are a little different than on the previous examples. It doesn't matter, but don't let that throw you if you just happen to notice it. We're going to get the difference for C. So 12 minus 10, 2. Minus 12 minus 10, minus 22, and so forth. And then we're going to square those deviations. And we're going to do the same for D. 9 minus 15 is minus 6. Minus 4 minus 15 is minus 19, and so forth, all the way down. We square for C, and 0.02 squared is 0.0004. Minus 0.22 squared is 0.0484. And we take all those squared deviations for C, and we add them up, and we divide by n, and we take the square root, and that gives us the standard deviation. So here we have the standard deviation for C. And here we have to do the same thing for D. So 0.06 negative squared is 0.0036. 0.19 squared is 0.19 negative squared is 0.0361. Do it all the way down, add them up. It says to add them up, divide by n, and we end up with a standard deviation of 0.121326. Now this is this. We're taking all these products, this part up here, this part of the numerator, all those products, and adding them up. So this line right here shows us the summation part. And then we divide by n, and that gets us to covariance. Now, what we have in this case is, in period 1, C is above its mean, and D is below its mean. So their product is a negative number. Most of the time it's a positive, but sometimes it's a negative. And when we add those numbers together, the more negatives we have, and especially the more negative these more negatives are, when we add them up, we get a smaller number. And right here, we have the correlation coefficient. So we add up all these products and divide them by n, and that gives us the covariance. And what this shows here is, if we take the covariance that we just calculated, and that's this number here, if we divide it then by the product of the two standard deviations, that would be this number here times this number here, we get the correlation coefficient. This is a Greek rho. So the correlation coefficient is a little bit more intuitive. We've got a little bit better idea of what is a high and a low correlation coefficient, because correlation coefficient only goes from and including -1 to +1. And a 0 means they're uncorrelated, meaning that there's no relationship. So I think correlation coefficient is more comfortable for most students, for most people really, just because the numbers are easy to deal with. If someone told me, well, the covariance is 0.01396, is that a high or a low? I don't know. But if they tell me it's 0.9382263 correlation, I know that's a high correlation. And most stocks are going to be fairly highly correlated with one another. One thing to note, what if we were just looking at C versus C? Not C versus D, but C versus C. Think for a second about what that looks like. Well, really, what it looks like, let me see if I can get these on the same page. What it kind of looks like is this. If you were to take off the radical here, and we would just say that's the variance, sigma squared, but if you took off this radical, you would have the sum of the RCT minus R bar C squareds divided by N. Well, that's what this would be. If you were comparing C to itself, C to C, instead of C to D, then for every period, whatever the difference is for C, that would be the difference for C. And so you are squaring that difference, and that's exactly what's happening here. It's just with standard deviation, we're taking the square root, and we don't take the square root here. But what this means is, and I ask you to remember this, is that the covariance of any series with itself is equal to its variance. The covariance of any series with itself is going to be equal to the variance of that series. So we have covariance and correlation, and we use them in portfolio theory. Now, you're not going to be expected to do what's on the next page, but don't turn it off just yet. This is called the Markowitz formula. This is saying that the standard deviation of a portfolio is equal to, and without going into too much detail, you have to take every asset and every other asset, and you have to take for every asset to every other asset their relative weights times each other, and then times the covariance between them. And you have to do that for every pair of assets. Now, when Markowitz came up with this in 1951, computers were obviously a lot slower, and this was not even really under consideration as a calculation. There wasn't enough computer time. But this breaks down to the two-asset portfolio. So this is for any number of assets, and this is just for the two-asset portfolio. And it says take the weight of 1 squared times the variance, or sigma squared. So for asset 1, its weight squared and its variance, plus asset 2's weight squared times its variance, plus 2 times the weight in asset 1 times the weight in asset 2 times the correlation coefficient between them times their individual standard deviations, and then take the square root of all that, and that gets you the standard deviation of the portfolio. And this just goes through the example on the previous page to calculate the standard deviation, and it's 0.120083304. Now, this isn't really a proof, but this is just showing how that would work if we forgot about all this stuff and just assumed, and here we've got a 50-50 portfolio. 0.5 squared is our weight squared, 0.5 squared is our weight squared. It could be 0.6 and 0.4, or 0.7 and 0.3, or whatever. What this does is it takes our set of numbers from the previous page and says, what if we had put half of our money in asset C and half of our money in asset D and gotten the returns on the previous page in each one of those? What would have been the return of our portfolio? Well, half at 12 and half at 9 Well, we could add them up and divide by 2, or we could multiply each one by 0.5 and add them up. And if we did that, we'd get 0.105. And minus 12 and minus 4 gets us minus 0.08. And 24 and 32 is 28. And 8 and 16 is 12. And 18 and 22 is 20. And so, if every period we rebalanced, and we would have to rebalance, if we didn't, after the first year, since the return of asset C was higher than the return of asset D, we would now have more money in C than we would in D. And no longer are we at a 50-50 portfolio. So almost everything that you see makes the assumption that you rebalance back to 50-50 every period. And that's what we've done here. And when we do that, we get a return, mean return of 12.5%. And if we calculate the standard deviation, 12.5%, well, here are our individual returns. So it would be 0.105 minus 0.125 is minus 0.02, and negative 0.08 minus 0.125 is minus, this is rounded to 0.21, but the calculation is carried out all the way. 0.28 minus is this, 0.12 minus is this, and 0.2 minus is this, but they're carried to I guess it has to go to three places, I guess. And then this says, well, we're going to square the standard deviation says we're going to square the deviation. So we've got mean value, and we take all the differences, and we square all the differences, and we add up all the squared differences, and we divide by n, and that gives us our standard deviation. So when we do it this way, we come up with this number, which is the same as in Markowitz's formula. It's not really a proof, but it shows consistency. Now we talk about beta and the security market line. And this formula just shows that beta for a security, let's say that this is my X value. Let's say that this is the stock market, because we're going to look at a security relative to the market, and we're going to pretty much assume that the quote market unquote is the stock market, often just measured according to the Standard & Poor's 500. So what this says is the covariance between these two, which would be the covariance between the security and the market, divided by the variance of the market, would equal the beta of the security. So here we have beta is equal to covariance of CD divided by the variance of C, and that gives us the beta of the security. And a beta of 1 is equal to the market beta, and a beta higher than 1 is equal to, this means that it moves up and down more than the market does, and a beta of less than 1 means it moves up and down less than does the market. And this is to calculate the alpha of the security. And the alpha of the security is, let me see if I can quickly find a different page. Well, when we plot the return to a security versus the return to the market, so I'll just call this I and that M. When we plot these things like this, so this is the return of 1 year of the market would be this much, and the return of the security this much. We plot that point. And then we do it for the next period, and the next, and the next, and the next, and so forth. And we get this scatter diagram. And we draw a line, or we do it mathematically, we draw a line that best fits these dots. And maybe it looks like this. And if so, it has a slope which is equal to the beta, and we show beta as a Greek b, and it has an intercept which we call the alpha. And so this is the formula for the alpha, and you're not going to be responsible for either one of these things. It's just this is what they are, and so when you're looking at when we develop into what is in the chapter, and we have to use this beta, we're going to apply this beta to another graph, and the other graph, this is just to sort of show in advance, the other graph is going to have beta here and return up here. And we're going to take the beta that we get from this graph and we're going to apply it to this graph. This is our security market line graph, and it's going to look something like this. And it has a slope, but it's not this slope. It's its own slope. So we take this measure of volatility, which just means how much does it go up and down relative to the market, and we take that measure of risk and apply it over here to the security market line, and we get a formula for that, which we'll go into in another video.